Hey everyone, welcome back to Calculus 1. This will be lecture 19 of the course, and in this lecture we're going to discuss optimization problems. So in the previous section we talked about curve sketching, which is definitely an application of derivatives. It's you can think of it as more applied in nature. This lecture is going to be all about real world application type problems. So we're going to go through a couple of examples, I think probably about 3 of them. And these are classic examples from Calculus 1. And so if you're a student who's thinking about going into physics, or maybe you are a physics student, or maybe you're thinking of going into engineering, these are the kinds of problems that you will run into over and over in your physics and your engineering coursework. Not these exact problems necessarily, but this kind of thing is pretty common. So let's jump into it. This we'll call section 3.7, optimization problems. Okay, and so our first example will be, well, before I get into that, actually, what do we mean by optimization? So optimization can, of course, mean a lot of things, but in the context of Calculus 1 and the context of differentiation-based optimization problems, a lot of times what that means is find a minimum or a max for a given function. Okay, so find a minimum or a maximum for a given function. That's what a lot of these are going to boil down to. Well, actually, all 3 of the examples we'll look at today will be involved in will revolve around finding a minimum or maximum. Optimization can mean other things in other contexts, of course, but in this context, that's what we're really after. So the roadmap will basically be, given a scenario. Okay, you want to identify a function that can be used to model the scenario, and then you want to find a max min of function. That's kind of more or less what we're up to here. Now, as you'll see, we'll get into some examples here. These can vary very widely, right? They can be quite distinct. So, I mean, this is a general blueprint of what we're up to, but it's the details can vary widely. So, let's take the first example. Let's start off with the first example. And so, in this example, we are playing the part of a manufacturer who is involved in the manufacture of boxes. Okay, so a box maker, and I always in my mind just imagine like a cardboard box maker, like someone building cardboard boxes. A box maker wants to design an open box with a square base. Okay, a square base and a surface area of 108 inches squared. Okay, so a box maker wants to design an open box with a square base and a surface area of 108 inches squared. So the question then is, what dimensions will produce a box with the maximum volume? That's our question. Now, obviously, you'd say, well, just make the box as big as possible. Well, that's where the constraint comes in, right? We have a constraint. The surface area of the box must be equal to 108 inches squared, right? It can't be less than that. It can't be more than that. That's the fixed constraint on the surface area, which means, obviously, that the lengths of the edges of our box are constrained as well, right? We can't make a box with edges 1,000,000 inches long, right? Because that would obviously exceed our surface area constraint. So let's draw a picture here. So we've got our box here, and it's an open box, right? So that means there's no top on the thing. It's also got a square base, which means that the base down here is x by x, whatever x happens to be. There's no constraint on the height of the box, right? So that's a different variable. We'll call it h. And what we're interested in here is maximizing the internal volume of this thing, right? The volume of the box. And so we know that the volume of a box like this would be equal to x squared, right? The area of the base times the height. So x squared times h is going to be the volume. Okay, so that's equation 1, right, that we're going to need. We're going to need that one. Now, this is actually the equation or formula, however you want to think about it, that we're going to want to maximize, right? So we want to maximize the volume given the constraints. And so what that will entail is identifying the derivative of this function v with respect to x or h, however we want to set it up, probably x, right? And so the fact that you have x and h together here is a problem, right? So this is where the other constraint comes in. So the surface area constraint. So let's have another equation that is the surface area. Now we know that that is equal to 108. We'll just leave the units off for now, but it's square inches. And we know that the surface area is going to be basically the area of the base, right? This bottom part, plus the area of this piece here, plus the area of this piece here, plus the area of the piece to the side, and the area on the very back. Right? And so a nice, concise way to write that would be x squared plus, well, you could write it like xh plus xh plus xh plus xh. Of course, a better way to write it would be to say that the surface area equals 108 equals x squared plus 4xh. Okay, because you've got x times h here. You've got x times h here. You've got one in the back. And you got one in the back on that side as well. So 4xh, and then you've also got the base, which is x by x. Okay, so now you've got v equals x squared times h, and s equals x squared plus 4xh equals 108. So those are your two big formulas to have to keep in mind. Okay, so now here's a trick that, as I said, if you're going into physics or engineering, you may have already seen this if you've taken those courses. But usually what you'll need to do is you have to figure out a way to combine the functions such that the constraint is introduced into the equation that you're trying to maximize. So in this case, the constraint is that the surface area needs to be 108. So I need to get this information here into this volume equation. Right, now the way to do it is to notice that x squared plus 4xh equals 108. Well, what that implies then is that 4xh equals 108 minus x squared, and h equals 108 minus x squared over 4x. And then this guy here can be plugged into this formula. Okay, and once we've done that, then the volume formula will contain the surface area constraint. It'll be a piece of the equation. Okay, so let's do that. So v equals x squared times h. Well, that is x squared times 108 minus x squared over 4x. Okay, and we could clean this up a little bit. And what we would end up with is the x's will cancel, and you'd have 1/4, and then we'll write 108x minus x cubed. Okay. All right, so this is what we need to maximize. All right, we want to maximize the volume, and this is how we've got the volume kind of set up. Okay, so then in order to maximize this, we're going to need to identify dv dx. Right? The derivative of v with respect to x. So that's the change in the volume with respect to the change in the length of x. Okay, and then as you change x, that will as you change x, it's set up in such a way that the surface area constraint will also be maintained. Okay, so let's calculate dv dx. And so that's d dx, just rewrite it here, of 1/4, and then it's 108x minus x cubed. Okay, so that's our derivative, and we can easily differentiate this. And so you get 108 minus 3x squared. Okay. And so then that means dv dx will equal, and we can kind of rewrite this a little bit, so maybe it's 27 minus 3/4 x squared. That might be a better way to write it. And so when we're trying to identify maximums and minimums, we need the derivative, and then we need to identify the roots of the derivative. So then we need to set dv dx equal to 0 and solve for x. Okay, so let's do that. So dv dx equals 0 means you're dealing with 27 minus 3/4 x squared equals 0. And so that means you've got negative 3/4 x squared equals negative 27. And that means you've got x squared equals negative 4/3 times negative 27. And now this looks like a messy product here, but 27 and 3, so 3 is 9 times 3 is 27, right? So these two cancel. You get a negative 9, and altogether you get a 36 here, which is a very nice number, especially when it's x squared equals 36. So that means x is equal to plus or minus the square root of 36, which is plus or minus 6. Okay, so we have two roots of this derivative. So two roots, x equals 6 and x equals negative 6. Now, what is x? Well, x is the length of the base of the box that we're manufacturing, right? So it's a length. Right? If we look closer at this, that's what x is. So it's important to keep in mind that that these equations are in relation to a real physical problem. So the length of the base of the box cannot be a negative number, right? So it can't be a negative number, so we can disregard this root, x equals negative 6, and we're really just interested in this guy. So we can see, basically that x equals 6 is going to be the maximum value. And we can use this root, x equals 6, to figure out what the other dimension, h, is. So we know length and we know width, we don't know height. Length and width are both 6, that's the base dimension. Now we need to know the height. And so we can use the surface area formula to find the height. So S equals, what was it? X squared plus 4xh equals 108. That's what we had, right? And so if we plug in 6 for x, we can force out h, can't we? So 6 squared plus 4 times 6 times h equals 108. Right, we can do that arithmetic quick, and we can see that h would be equal to 108 minus 36 divided by 24, which is 3. Okay, so there we go. So that is the height of the box. So the dimensions are 6 by 6 by 3. And of course you can multiply those together to identify the volume. Right? 6 times 6 is 36, times 3 is 98 or something like that. Yep, so there you go. I think it's 108 actually. Oh, 100. No. 6, well, 6 times 6 is 36 times 3. 108. Interesting. Okay, so the volume is also 108. Okay, all right. So that's our first example. So here what we did was we had an open box and we figured out 6 by 6 by 3 produces max volume. And of course, that produces the max volume under the constraint that the surface area is 108 inches squared. Okay. So, all right, very good. So that's the first. That's the first example. Next up, let's take a look at something that is quite a bit different. So from the one we just looked at, this is more like a this is this kind of problem that you might expect to see more in a math class, right? So this one says which points. So given the graph of y equals 4 minus x squared and the point 0, 2, which points on y which points on y equals 4 minus x squared are closest to the given point? Okay. Given the graph of y equals 4 minus x squared and the point 0, 2, which points on y equals 4 minus x squared are closest to the given point? Okay, so let's draw a picture here. And this picture won't be perfect, but it won't be too bad. So, okay, so this is obviously the x-axis and the y-axis. Now, the given point is 0, 2, so that's right here. Okay, so that's 0, 2. And this is, if you look at y equals 4 minus x squared, you'll notice it's just a quadratic equation with the y-intercept at 4. So it's up here, 1, 2, 3, 4. It intercepts right there. But this one is not, I mean, it would be obvious if this was a normal quadratic graph of a normal quadratic where it was kind of open, concave up here. But because it's the coefficient on front of x is negative, it actually opens down. Okay, so it looks more like this. And this won't be a perfect picture, but hopefully it's not misleading or anything. It kind of comes down like that, right? So the question here is, obviously there's an infinite number of points on this function. Which point or points, as the case may be, are closest to this point, right? So you might intuitively say, well, based on the way you've drawn this, maybe it's like that. One of those 2 points, or maybe it's it's not the top point. And if you actually graph this, you'll be able to see that it's definitely not the top point. But maybe it's some point off to the side, or maybe, I've drawn it really badly and it's actually the point that's like exactly horizontal, right? But there's going to be some point or points. In this case, it's probably 2 points, right? Because it's symmetric about the y-axis. There's going to be 2 points that are the closest to the given point. And that's our task, is to find that, to figure out what those points are. Okay, so we want to minimize the distance between some xy and 0, 2. Got xy and 0, 2 is given. Xy are not fixed. We want to minimize the distance. So you may recall the distance formula. You've probably seen this in pre-calculus or maybe in even high school algebra. So D equals, so it'd be like x1 minus x2 squared plus y1 minus y2 squared, and then it's the square root of that. And that's, of course, if you have 2 points, x1, y1, and x2, y2, and those are the points you're trying to minimize, or not, those are the points you're trying to identify the distance between. That's the word and there, sorry about that. So you've got 2 points, x1, y1, and x2, y2, and then this formula tells you the distance between them. All right, so that's the formula that we're going to use here, and that's what we're going to use to minimize this. Okay, so let's plug our given point into this formula and see what we've got. So D equals, so let's just call this x1 and, sorry, we'll call this x2 and y2. So you're going to have x minus 0 squared plus y minus 2 squared. So that's the square root. We need the square root of that. And so this is what we want to minimize. Now, similar to the previous example, we've got x and y in here. There's also a constraint, right, on x1, y1. So this is the side that we're letting vary. This one is fixed at 0, 2. This one we're letting vary, but there's a constraint, right? The x's and y's that are must combine to satisfy. They must satisfy y equals 4 minus x squared, right? They have to actually be on the graph of this function, right? So let's plug this in for y here, and that would be a way of kind of baking in that constraint. Okay, so what we'll use is D equals x minus 0. I'm going to leave the 0 there just for now so people can follow exactly what I've done. Now instead of y, we're going to put 4 minus x squared in there. Okay, all right. Okay, so all we did was we took the y here and just plugged in 4 minus x squared. Okay, now we can go ahead and we can simplify this expression. And so when we do that, we get x squared, and then here you're going to have 4 minus x squared minus 2. And so that's just going to be, what, 2 minus x squared. And that should be a plus there too also. Plus 2 minus x squared squared. Right, so it looks like that. And then we can expand that further, and ultimately we get x to the 4th minus 3x squared plus 4. Okay, and that's just expanding this. You got to FOIL this out and then combine like terms. But you can see you're going to get an x. This will be an x, x to the 4th, right? And then you're going to get minus 4x squared plus an x squared gets you that one, and then the 2 times 2 gets you the 4. Okay. Okay, so what we want to maximize, we want to minimize D equals x to the 4th minus 3x squared plus 4. That's what we want to minimize. And in doing that, we will implicitly be finding the x value that is the minimum that produces a minimum distance between 0, 2 and this graph of y equals 4 minus x squared. Okay, so we're going to need the derivative, aren't we? So let's calculate d prime. I'm going to write d prime, and then that's ddx of this, which I'm going to write as x to the 4th minus 3x squared plus 4, 1/2 power, like so. And we can differentiate this, right? This is going to require the chain rule, but we can do that no problem by now, right? So 1/2 x to the 4th minus 3x squared plus 4, negative 1/2 power, and then times this derivative inside, which would be 4x cubed minus 6x. Looks like that, right? And so let's clean this up a little bit. So we'll get let's see, it'll be 4x cubed minus 6x all divided by 2 divided, sorry, that's a square root. And then it's x to the 4th minus 3x squared plus 4. There we go. And so that's our derivative. Now, when we're looking for relative maximums or minimums, in this case minimums, we need to set d prime equal to 0 and solve for x. Okay, and so d prime equals 0 implies that this is equal to 0. Right? And so what happens here, if we multiply both sides by this denominator, right, we get this side, it cancels out, and then over here it's still just 0. So you get 4x cubed minus 6x equals 0. All right, that one's easy to get to find the roots of. And so when we do that, we have 4x cubed minus 6x equals 0. And we can solve this by, let's see, we'll factor a 2x out. So 2x, and then here you'll have 2x squared minus 3 equals 0. So one of your roots is 2x equals 0, and that means x equals 0. That's a root of the derivative. And then the other one is found using this side. And so that means 2x squared minus 3 equals 0, 2x squared equals 3, x squared equals 3 halves. X equals plus or minus the square root of 3 halves, like so. Okay, so that's the other one. So we basically have 3 roots of the derivative. Now, all of them are relevant in this context, right? In the previous example, we said, well, we got to throw out the negatives because that doesn't make sense. You can't have a negative length. But for this problem, we're dealing with, basically each of these roots, 0, negative square root of 3 over 2, and positive square root of 3 over 2. Those are all just potential x values. So like there's 1, there's 1, there's 1. All right, which one of these produces the minimum? Well, that's what we'll try to figure out here. And so if you graph this thing properly, you'll notice that this one is not a minimum. Okay, you'll notice that this one is not a minimum, right? These two, however, are minimums, right? These are our minimums, and because of the symmetry in the graph, they're both going to produce the same distance. They're both going to produce the same distance here. And so they're both going to be minimums. They're going to be equivalent, right? And so we can use them to identify the points on the graph that are that produce the minimum distance. And so that's just a simple matter of plugging them into the formula. So if y equals 4 minus x squared, then we can plug each of these in. So y would be 4 minus square root of 3 over 2 squared, and y equals 4 minus negative square root of 3 over 2 squared. In both cases, you're going to get 5 halves. Okay, in both cases. Excellent. Yeah, so you can see, you can do that work on your own. But so basically, so the points 3 halves, square root of 3 halves, comma 5 halves, and negative square root of 3 halves, 5 halves produce the minimum distance. Okay, so basically these points are the closest they're on y equals 4 minus x squared and are the closest to the point 0, 2. Okay. So those are your points. Okay. Very good. All right. Good. Good. Let's do one more example. One more example. And this one will be maybe possibly a little bit more involved, but it's a good one still. It's kind of more real world example again, a physical problem. So in this case, I'm going to just draw the picture and describe what's going on here. So we've got two posts in the ground. They're stuck into the ground. One of them is 12 feet. Okay, and then the other one is some distance off, and it's taller at 28 feet. Okay, so this one's 28 feet high. And this one's 12 feet high. Now, obviously, they're sitting in the ground, right? They're posts buried in the ground. Now, somewhere, so in the distance between them, we should write is 30 feet. Okay, so the distance between them is 30 feet at ground level there. Now, each of them is going to be, there's going to be a wire connected to the top of each of them that comes all the way to the ground. So I'm just going to put a marker here, right? Let's say that's some stake in the ground. And it's going to be connected to a wire that goes all the way to the top of that one and all the way to the top of that one. Okay. Now where this is at in the ground can vary. It could be really far over this way. It could be further over this direction. It could be anywhere in between here. Okay. So we're not worried about any kind of structural integrity of these wires. They don't hold them up or anything. It's a wire attached to the tops and it comes down to the ground at the same point. But it could be anywhere on this continuum. Okay. The question is, where should the stake be placed in order for the length of wire needed to accommodate this? Where should the stake be placed to minimize the length of wire? Right? You might imagine, right? If I put the stake right down here, very close to this base, then you got 12 feet here, but then this might be longer, right? Conversely, if I put the stake right down here, I got 28 feet, and then this is longer than it needs to be, perhaps. And somewhere in the middle is going to be the sweet spot where the stake is positioned in such a way that the length of wire is minimized. Okay, so I'm going to call this Y and this Z. So Y plus Z is the total length of the wire. Now, we're going to denote this as X, right? That's the distance from the 12-foot pole to the stake. And then the whole distance is 30, so I'm going to call this 30 minus X over here. It's a kind of a convenient way to notate these things. And it's very useful if, rather than having X and then some other variable over here. Okay. So here's what we want to minimize. So we want to minimize W, that's the length of the wire, which is going to be equal to Y plus Z. So whatever Y is plus Z, that's the length of the wire, and that's what we want to minimize. We want to use as little wire as possible. Okay. All right, now let's break this down because obviously you will have noticed that we're dealing with some triangles here. All right, so we've got a 12, an X, and a Y triangle, and then we got this other one over here, which they're both right triangles, right? Right triangles. And this one is 30 minus X and Z and 28. Okay. So we can use so the problem here is that Y and Z, right? We don't really want to, we can't do anything with this, with W equals Y plus Z. If W is expressed in terms of X, we could differentiate it and minimize it. But right now we haven't. That's the big challenge, right? We have to recast this expression in terms of x only. Okay, but the good news is both of these triangles contain x, and we can rewrite y and z in terms of x using the Pythagorean theorem. So let's just recall that. You will obviously have seen this. Given a triangle A, B, C, right triangle, we know that a squared plus b squared equals c squared. And that's what we'll want to use here. And so let's start with this guy here. So this one we'll have y squared equals 12 squared plus x squared. So that means y equals the square root of 12 squared plus x squared. Okay, so that's good. So we've got that piece. Right, now we'll be able to take that, plug it in here, and then that piece at least will contain x only. We can do the same thing for this guy. Right here we can say z squared equals 28 squared plus 30 minus x squared. And so z equals the square root of all that, like so. Okay, so now this one here will be plugged in for that. So let's just write that down just so that it's clear what we're headed towards. So this is coming in for that, and this is coming in for that. Okay, now what will we have accomplished in doing that? Well, we will have accomplished that w is now a function of x. Okay, we'll also have we will have built in the constraint of the 30, the distance here being 30, and the 28 and the 12, right? So all basically the constraints on the triangles are going to be now built into this w function as well. All right, so that's the name of the game with this. You want to build a function up that includes all the constraints and is differentiable and written in terms of a single variable, ideally. Okay, good. So now let's do that. Let's figure out that w. So w equals y plus z. So that means w is equal to this. So 12 squared plus x squared plus this. 28 squared plus 30 minus x quantity squared. Like so. All right. And let's go ahead and just do a little bit more work to this. Let's get rid of all the 12 squared, the constant square. We can sort that out. So w will equal x squared plus 144 plus, now this thing here, if you spend a little time, you have to get out a calculator and kind of calculate some of these squares. They're a little big, but it's basically x squared minus 60x plus 1684. So kind of a bigger numbers here, but I mean, they're just numbers, no worries. So next we need to find dw dx, right? So w is now written in terms of x. If we differentiate it with respect to x, then that will give us the opportunity to find the minimum or the maximum value of w. In this case, we want to find a minimum. We want to minimize w with respect to x. So, so dw dx is going to be equal to d dx of this guy here. And I'm going to write it like this. Of course, just makes the differentiation a little more obvious what needs to be done here. X squared minus 60x plus 1684 to the 1/2 power. All right, now we can come through here and differentiate this real quick. 1/2 x squared plus 144 to the negative 1/2, and then we differentiate the inside, which becomes 2x. Okay, and then plus, again, similar in structure, x squared minus 60x plus 1684 to the negative 1/2. And then here you're going to get 2x minus 60. All right, so that is the first pass. And now, of course, we can clean this up a lot, right? So this piece here is -1/2 power, so that'll be in the denominator as a square root. The 2's will cancel. Okay, and so here I just get x over the square root of x squared plus 144. And then plus, now similarly here, this is all going to be in the denominator, and you've got a 2 that'll cancel here and here. So that's good. And so you'll have x minus 30 on top, and then x squared minus 60x plus 1684 square root on the bottom. Okay, now this, of course, we'll just rewrite it here. This is dw dx. That's your derivative of w. Okay, so now that we found the derivative, what's next? Well, next up is to set the derivative equal to 0 and to solve for x. So set dw dx equal to 0 and solve for x. Okay, that's the next step here. So it's kind of it's not that it's like super hard to deal with this. It's a little unwieldy because you've got these enormous square roots in the denominator like this. And this isn't an example like the previous couple we've seen where you can just kind of multiply it through and get rid of them and disregard them. Here you actually have to deal with them, right? So basically, because this is a sum, you can't just multiply both sides by this. You can do that, but first you have to get a common denominator and make this a single term over here. And so that's where it gets a little messy. So basically it's got to be x times this like so, plus x minus 30 times this, like so. And then the whole thing, of course, is over this and x squared minus 60x plus 1684. And that's all equal to 0. Now that looks really ghastly, but the good news is that this denominator, once it's in this form, you can multiply both sides by this whole expression, and then these will cancel on this side, and of course 0 times that is 0. So the net effect here is that you just get this. Which in and of itself is not the most beautiful thing to deal with, but it's not as bad. Okay, now you still have these big square roots. How are we going to deal with that? Well, what you can do is you can take this guy here and throw it on the other side. You basically got two terms. So if you have one term on both sides, it's very easy to work with. So we're going to do that quick. So I got this one here, and then I'm going to move this one over to the other side of the equal sign, and then you get this. Negative, yep, x minus 30, and then the square root of x squared plus 144, like so. Okay. Now, the advantage of doing that is once you've done that, then it's really easy to just square both sides, like so. Right, and then that'll dump the square roots. And so what you'll end up with then is x squared times x squared minus 60x plus 1684. And that'll be equal to, this becomes a positive, and this becomes, so, well, let's move the negative through here. So it'll be 30 minus x squared, and then this guy here will just be x squared plus 144, because whenever you square a square root, of course, right, that's the whole point of doing it this way. So then you've got this. All right, now while they're separated like this, let's go ahead and expand each side here. Okay, and so over here you're going to get x to the 4th minus 60x cubed plus 1684 x squared. Okay, and I actually did this ahead of time just because I didn't want to have to resort to the calculator here, but we can also do the same thing over here, right? So first you got to square this term, and then you'd have to distribute everything and FOIL everything out. But what you're going to end up with on this side is x to the fourth minus 60x cubed plus, and here's where it gets kind of messy, 1044 x squared minus 8640 x plus 129,600. So you've got these big constants here. Not a problem though, right? So not a problem. These are all computation here. Now let's bring everything back to the other side and consolidate. And I'm just going to cut right to the chase on this one. But you can obviously pause the video and sort this out, all this algebra out. But ultimately what you end up with is 640 x squared plus 8,640 x minus 129,600, and that's all equal to 0, right? So I know that's but I mean, you can see this is just algebra, right? You're just combining like terms. The x to the fourths drop out, the x cubes also drop out. The x squareds combine to get you this guy, 640. And then the other ones are basically the same, untouched. Okay, and now here's where you're going to want to get out a calculator or go to Wolfram Alpha or something. You're going to have to figure out some way to deal with this. These are big coefficients. But you can factor a bit here, right? So 320 times x minus 9 times 2x plus 45 equals 0. Okay, and so the 320 doesn't matter. But you've got x minus 9 equals 0, so that means x equals 9. That's a root of the derivative. And the other one is 2x plus 45 equals 0, so x equals negative 45 over 2, which is approximately negative 22.5. So that's another root. So you've got these two roots, and the question is which one matters and which one is useful. So the negative here, right? So remember what x is. X is the distance between the first stake, or sorry, the pole and the first stake. So you got the pole here, the stake here. X is a positive distance, right? So this doesn't make sense. So we're going to roll with this. Okay, so x is equal to 9. So 9 is the value of x that is going to minimize dw. Okay. All right. And so 9 is a critical value. That's going to, and you can do the work by plugging in test values on either side of it to see that it is in fact a minimum. But basically, once you have that, you have the problem more or less in hand. All right. So let x equal 9. And from that, you can see that the wire should be staked 9 feet from the 12-foot pole, and the wire length can be deduced from this. Well, first you got to figure out how far from the 12-foot pole, right? So remember, you've got your 12-foot here, and you had your 28-foot over here, right? This whole distance is 30 feet. Right, and so we're saying that it's 9 feet from here over to the stake, and so that would mean this would have to be what? 21, right? Okay. So 30 minus x. Okay. And so you can use this to figure out what each of the pieces are. So for example, you had the first triangle, which was 12 by x equals 9 now, right? That's this side here. And then, so this was y. And so y would be equal to the square root of 12 squared plus 9 squared, which is the square root of 144 plus 81, which would actually give you 15, ultimately. Okay, so this length of wire is 15. This other length of wire can be figured out as well, right? So here you've got the triangle. It looks like this. So this is 21, this is 28, and this is the z. Okay, so z would be equal to the square root of 28 squared plus 21 squared. Okay, and when you plug all of that in, you should have 25 feet. Should get you a 25. Okay, and so that means this length of wire is 25 feet. Okay, perfect, perfect. So that's the setup, and then of course, I guess technically W is equal to Y plus Z, and so that turns out to be 15 feet plus 25 feet, so 40 feet in total. Okay. Very good. Very good. Okay. All right. I think I did that right, didn't I? Yeah, I think so. Okay. It's possible I made a mistake here in the end, but so that's it for this section. Very good. So these are just a few of the many, many examples of optimization problems. You can jump into any calculus textbook and find a whole bunch of these. And these are very, very useful, very if you think about it, being able to calculate this kind of stuff would be basically impossible without calculus. So, well, in some scenarios, you might be able to work it out just algebraically, but most of these examples we've seen would require being able to minimize the derivatives. So, very good. So that is the end of the lecture. And that is actually the end of Calculus 1. Now, this channel will I'll also have Calculus 2 available. So if you're interested in continuing on with this coursework, if you find my method of instruction useful, then Calculus 2 should be available now or shortly. So, all right, take care.